look at the sun. Okay. So what about the sun? Of course, the sun is a star. We're going to see when we study stars, the sun is like an intermediate star. Right? You'll see kind of a spectrum of stars. It's kind of in between. And the sun. When did the sun turn on? It was a. How long ago?
4.6.
Very good. 4.6 BYA. Not that doesn't even bring your own alcohol. That means 4.6 billion years ago. Right?
What?
Right. So if you round 4.6 to 5 or so. So actually, like this says, okay, we have about 5 billion, oops, I'll write it up here, about 5 billion years left.
So it's supposed to stay on for 10 billion years.
Right. Yeah, 5 plus 5 is 10, exactly. And that's kind of the way that goes for our middle of the road star. And actually, we're going to see that it depends on kind of when a star first started its life. Like, if it's a light star, if it doesn't have much mass, or if it's a really heavy star, it has a lot of mass. That kind of says that it's going to be 10 billion years, or 1 billion, or 100,000, or 100 billion, or a trillion years.
So then what's going to happen?
If the sun keeps going, we're going to burn up.
So what the sun is going to do is actually, the next stop is it's going to swell.
Suck us all in.
Yeah, it's gonna. I think it's gonna swell out to the orbit of Mars, and so yeah, like the surface of the sun is gonna be out to Mars. So yeah,
We're going to die.
we'll be part of this. Yeah. We got some time.
Now you can come back. No, reincarnation.
Hopefully, I'm done by then. But the thing about
We'll
our
be dead like 3 times by the time they come.
few generations.
Yeah.
But the thing about our sun is not gonna blow up. So our sun is I talked about these different stars, so our sun is like here. We have these light ones, we have these heavy ones. Well, depending upon how much mass they have, kind of drives how it ends its life. Our sun will not blow up. Instead, it's just gonna swell, right? And then the little corpse that's left behind is gonna turn in, then it's gonna contract, and it's gonna be like what we call a white dwarf, which is not a star. It's a corpse of a star, a white dwarf. Okay, so it's gonna swell, and then it's going to blow away those gases. It might make what we call a planetary nebula. Okay, and this thing's going to be a white dwarf, so that's us.
And then we're going to have to start on the new nebula.
That's right. That new nebula can be, make another star, exactly.
I think we got to use our imagination.
So if you think, speaking of imaginations, if you think about like people a long time ago, like we didn't always know about fire, and it's interesting to think about early people figuring out fire and capturing fire and all that.
Wow. Yeah, that'd be
Right? That's
right.
cool.
I think so. Did you say it was? No, this is the off topic people.
Okay, hold about that,
I
right?
will.
So the thing about fire is, what if our sun was what if our sun was just like a fire? Well, here's the deal. Based upon how much mass our sun has, it would last. Okay, it would last 10,000 years. That's not fitting with the 5 billion and 5 billion more to go, right? So that type of mechanism for creating heat, it can't just be like a fire, okay? So here's another way to get heat, like our sun's putting out. Another way to get heat is basically take something big, like our solar nebula, and squish it down. That's converting gravitational potential energy into kinetic energy. Like our solar nebula did that, and actually that's in part why our sun's so darn hot. Well, you could do that, but that would give you 25 million years. And some of you guys already know how our sun is powered, and here's how our sun is powered. We're going to be talking more about it. Our sun is powered by nuclear fusion. Our sun and all stars have nuclear fusion going on in their core. Okay, nuclear fusion. Now, have you ever heard, like, you think the word fusion, to me, when I think of fusion, I think of fusing things together. Like, if you want to weld something, you fuse them together. So that's exactly what happens in the cores of stars, nuclear fusion. This is Einstein's equation. E stands for energy. M stands for mass. What does C stand for? We run into it before.
Wait, what?
C stands for, and it doesn't have the letter C, or it doesn't have the letter C in its name.
It doesn't have the letter
It's a
C.
speed, right. C stands for the
Constant.
speed. The C stands for the speed of what?
Speed of light.
Speed of light, yep. Is the speed of light very big a number?
Yes.
Yeah. It's like 300,000, is it kilometers per second? That's how fast light travels. Okay, so you take that, 300,000 km per second, and you put it in here, you take the mass, and that's how much energy you get.
Well, it has to be squared, so it'd be.
Right, squared, thank you. Square that term. Yeah. So the point is just a little bit of mass makes a lot of energy. So we'll be talking more about nuclear fusion. Now, the thing about fusion is if you've ever seen a video, and I don't know how to make this real to you, but in the middle of the sun, okay, most of the sun is hydrogen, and in the middle of the sun, it's very hot. So what happens to, how fast do particles move when they're very hot?
They get the boom, 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 boom.
Yeah, they get the boom, 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 boom. They get very fast. If they're very hot, they're very fast.
Yeah.
And the other thing about the interior of our sun, and it's the same thing with other stars, is it's very squished together. So high pressure squished together and very fast, very hot. And that means that when hydrogens run into each other, they connect. And as they connect, they make a new element. So what is He stand for?
Helium.
Helium, yeah. So two hydrogens basically make a helium. And in doing so, if you were to measure it afterwards, after the fusion occurs, you are going to lose a little bit of mass. So that mass is what's converted to energy. That's nuclear fusion in a nutshell. All right. So here we go. There's actually two types of fusion. I'm going to run them both past you. So this was the one I talked about. Can you see the two particles, the green particle and the white particle? They're going together to make a common particle. So that would be our hydrogen plus our hydrogen making helium. This is the other type of fusion. What's the difference here? What's this other one do? What's that? It's more of it, yeah. This is called, have you ever heard of splitting the atom? That's what this is. Okay, so this is splitting the atom. So this is fusion, and I hate it, there's too many F's. This is fusion, this is fission. Have you ever heard them talking about fissionable material? Like, ooh, better watch out, and it's true. Fissionable material is material that actually will decay, break apart into two smaller pieces of an atom. Then these are what we call the nuclei, these are the centers of the atoms, and create a lot of energy. So you can get energy both of these ways.
So the fusion is turned into two nuclei.
So the fusion turns into one nuclei. So here we have two turning into one. This is fusion. The fission takes one and turns into two.
Oh.
Yeah.
Okay.
Yep. So the second one's fission.
Fission.
Fission, yep.
Like vision.
Like fission, vision.
Vision.
Fission, yep.
Vision. But like vision.
Vision, like vision, fission, yep. So this is kind of a close call. So here we have the two little red those two little red things. Think of those as hydrogen atoms. Now they're close call because they don't connect. Why don't they connect? Why don't they go to fuse to form helium? Well, maybe the pressure isn't high enough. Maybe they're not moving fast enough. Okay, those are two important conditions in the cores of a star like our sun. What do you think? Did they connect here? Yes, they connected. This is showing before, this is fusion, and this is showing after. So they did connect. This is fusion, this is unsuccessful fusion, basically. So no, yes, no, yes.
Is that not drawn? Not drawn here?
There's missing that drawing.
Yeah.
What do you guys think? You think you're gonna like the PowerPoint slides?
The last one
Not
is
sure.
very more interesting.
Okay.
The different planets. Probably because it was just different planets when you got the different.
Yeah. No, I don't mean the subject. I meant having the slides.
Oh yeah.
Okay. All right. So yeah, I don't think you guys have this one either. Okay, but But this is kind of showing you from left to right. You don't have all these little boxes. They're showing from left to right the fusion process that I've been talking about.
Okay, so
And it's a little more complicated than just taking hydrogen plus a hydrogen, fusing, a hydrogen plus a hydrogen, fusing together and making helium. So I'm going to show you a little bit behind the scenes. I'll try to tell you what you need to know. So how many hydrogens do I have up here?
4.
4, yep. And so actually, as it turns out, you actually need 4 hydrogens to make 1 helium. And I'll kind of show you what that looks like. So in chemistry, we kind of write these chemical reactions with an arrow. So does this make sense? You read them from left to right. So this is what you start with, 4 hydrogens. This is time, give a little bit of time, let them react, and this is what you end with, the 1 helium. So here's kind of behind the scenes. This is why you need, these P's stand for the hydrogens. That's actually just what we call protons. So these are the hydrogens combining together. Do you guys see this little escaping particle right here? Okay, that escaping particle is a neutrino. And actually, we look for those neutrinos. So do you see this little squiggle here? Gamma ray. Does that seem like it could be electromagnetic radiation? Yep. So that's energy that's released. So we make these 2 blobs, and these 2 blobs come together, and they make, what's this thing at the end here?
Helium.
Helium, very good. Where is my, I've been using it, and then I didn't have it. All right, oh well. So on the next slide, I actually have, or the next 2 slides from here, I actually kind of show you in a nutshell what I would ask you on a test, what that looks like. But this is important. Here's the deal. If I go back to E is equal to mc squared, what's m?
Mass.
Mass, exactly. So this is what our sun's doing. So basically, like the slide says, our sun is getting lighter and lighter. By how much? Well, I know a ton's pretty darn heavy. So each second, 600 million tons of hydrogen are converted to 596 tons of helium. So how much mass is left converted each second? Do that math, guys. I got 605.96. 605.96.
What is to what?
Do the math. How much mass? So I start with 600 million tons of hydrogen, and I end up with helium, but I've only got 596 million tons. So how many million tons are not there? What's that? 4. So 4 million tons per second. 4 million tons per second. 4 million tons per second is, and we could actually plug that in here. Yeah, I could plug in 4 million tons, convert it, or take it times speed of light squared, and that's how much energy the sun's putting out per second. See how that kind of works? Start with hydrogen and with helium. Same mass? No, missing 4 million. So here's a funny little cartoon. I thought it was cute. So with this in mind, this couple actually knows that the sun is losing each second 4 million tons. And so what they said is they're kind of conversing, and the guy in the chair says, is it still there? And the woman at the window says, yeah, it's still there, but it's losing weight. So anyway, I just think that's funny. So this is actually in a nutshell. If I was you, you can put the star right here if you want to, because there's all sorts of stars that you want to. Since you guys had the PowerPoint slides, I would put. So somehow, some way, I'm going to ask you, what's the deal with the nuclear fusion going on in the core of the sun? And it kind of goes this way. What goes in? 4 protons. Protons, if you want to put hydrogen, you could. 4 protons, I'll put hydrogen equals 4 H's. And what comes out? 1 helium, 2 gamma rays, 2 positrons, 2 neutrinos. No, anyway. What comes out is kind of a mixed bag, okay? But you basically get your helium, like we've been talking about. You get your gamma rays. I'm going to put energy there. Your gamma rays are your energy. Positrons and neutrinos, I'm going to put a little, in music, when we want to make sure we look up at the conductor, we put a little eyeglass there. That's my little eyeglasses. So in other words, the eyeglasses are saying that here on Earth, we look for the presence of neutrinos to support what we think is going on in the core of the sun. Have we ever been to the core of the sun?
They're kind of like our red flags, pretty much. Like we need to look for those to see what's
Yeah,
going on.
red flag to me seems like it's a go, no-go thing, but so they're an indicator, because red flag means, I don't know, but yes, they're definitely an indicator of, they support our hypothesis or our theories. Yep. And they're hard to get. Neutrinos are hard to catch because they go through everything, so. All right. So E is equal to MC squared. That seems like a good test question too. What does the E stand for? What does the M stand for? What does the C stand for?
Right, I bet you.
So you told me that the hotter something is, the more it pings around.
Yeah.
So actually all gases ping around. So here, as you guys are in the room, you're like kind of 80-20, nitrogen, oxygen, both gas particles. So they're pinging around. I just love gases. They're awesome. The more you heat them up, the faster they go. So this is kind of showing you. Now, does it look like there's nuclear fusion going on in that box? Does it look like there's fusion going on in this box? Remember, fusion means they're connecting and they're making heavier nuclei. No?
There could be. It just doesn't.
Yeah, there could be. How would, if there isn't, how would we get nuclear fusion to go on in that box? What are the two things we need in the core of our sun?
You could decrease the mass.
Decrease the mass.
I mean the size of the box to make it
Decrease
smaller.
the volume of the box. I like that. Squish them together. That's decreasing the box volume is squishing together more pressure. What else? Very good. That's one. Pressure. Decrease the volume. What's the other one?
Most particles.
Speed up the particles.
Speed them up. How do we speed them up?
Heat them up.
Yep, two things. Pressure and heat. Yep. And when we switch gears from our sun to other stars, we're going to see that those are the two things that other stars need in order to turn on. All right. So here's the deal. So this would be how our sun is structured. So first off, where do you think is the hottest temperatures and the highest pressure? Would it be in that center region or would it be on the outside? Where's the greatest pressure and hottest temperatures in the sun? Right there. The inside, yep. We're actually going to call the inside of the sun its core, which makes sense. Okay, so in its core, we've got, that's where we have the hydrogen combining to form helium and releasing gamma ray energy. And I think that the video we watched on Friday might have touched on that. Those gamma rays that are creating the core, they have all this energy, and so they're out of here. But it's kind of an interesting sort of thing. We'll talk about how long it takes that energy to get out to the surface. But when I go like this, okay, so if this is the core, this is where my fusion is happening. So I have an outward pressure of energy. So I'm going to put energy going out. Now, like that this thing also says, we always have, what's this? Starts with the letter G.
Gravity.
Gravity, very good. You know, gravity's here on Earth. Gravity actually tethers us to the Earth. Gravity is associated with the planets. They're squishing all the planets to the planet's core. Gravity is associated with the sun. So here's the deal. And we're actually gonna be talking more about this with other stars. Is gravity, if gravity was all that on the sun, our sun should be shrinking.
Oh, shoot.
Okay? Our sun should be shrinking. If the core's energy were all that, our sun would be expanding because we have it expanding because of energy, we have it contracting because of gravity.
Okay, let me write that contraction.
Yeah, contraction because of gravity. So anytime you see a term called equilibrium, like you see this equilibrium up here, it means two things are equal.
You said it would swell up because of core or something?
It would swell up, yeah, it would swell up, and actually we see this on some stars because the outward pressure, the swelling part takes over. So, yeah.
From the core?
From the core, yeah. Now, I think we might have talked about in physics, they use the direction of the arrow and kind of the length of the arrow to the direction to show of the arrow to show what direction the force is going, and the length of the arrow to show how strong it is. So notice that I have, let's see, oh, I better fix this. I have 1, 2, 3, 4, 5 gravities, and I have 1, 2, 3, 4 outward from the energy. So I better add a fifth one. And my point here was to try to kind of show you that they're equal. So equal in, equal out. It's what we call hydrostatic equilibrium. And it's not unique to our star, but it makes it stay the same size. So that's what I'm going to add to this. I like writing red on black, so watch. Stay same volume. How's that? Because size kind of indicates mass. All right. Now I meant to bring in my little lava lamp, but my beta fish is enjoying it this morning, so, and he didn't have it over the weekend, so. But anyway, what a lava lamp is, okay, what a lava lamp is basically at the base it's heated, okay, just a light bulb that heats it, and then it has, next to the bottom, it has some sort of gooey, sort of dense, fatty probably material, that it gets hot, and as it gets hot, that blob expands, and as it expands, it actually becomes less dense than the stuff around it. So what happens to it? Exactly. So we see this a lot, and that creates what we call a part of a convection cell. So it expands. Okay, now what happens when it gets to the top?
It starts to separate.
It starts to separate. What do you think happens because of its proximity to the heat? What happens to its temperature? Like that?
It's like really, really, really hot.
Well, the temperature, it's gotten farther from the heat bulb.
So it's gonna start to cool down.
Yeah, it's going to start to cool down, exactly. And the fact that it cools down makes it come together and split apart a little bit, but you see it sink.
Yeah, it goes
Yeah.
down.
So it expands, then it's going to get here toward the the light bulb, and it's going to expand, it's going to rise. Okay, cell phones away, guys. Thank you. And then sink. Okay, so that actually creates what we call a convection cell. There are 3 layers to the sun's inside, and that is actually, that's the top layer, the convection cell. Underneath the convection cell is what we call the radiative region. Now this would be I'm going to put the radiative zone. You're going to see it here in a minute. Oops, goodness. Radiative zone. Check out these times down here. Oh, it must be in the next slide. So this is this energy I put right here. That energy is kind of those squiggles. So that's after it's left the core, and it's kind of like if you've ever played telephone where you tell somebody something and they tell somebody something and they tell somebody something, telephone. It's basically kind of getting the energy out. And that's what you're seeing, kind of particles bumping up to particles, sharing their energy, losing some, getting the energy out.
I never played that way.
What's that? You never played that game?
I did. I've always messed it up.
Naya.
I did.
Over here, I'm going to talk more about this random walk. I don't know, does it look like a random walk? So how long does that random walk take? And actually on the video we watched on Friday, it talked about how long does it take a little bit of energy that was created in the core to work itself out to the surface of the sun. And this is the ballpark you're looking. some 100,000 to 1,000,000 years for it to go from the core to the surface. All right? That's a long time. Does anybody remember once it's at the surface of the sun how long it takes to get the Earth? It's
a lot of light years.
more than 1 minute, but less than 30 minutes.
8 minutes.
8 minutes, yep. Once it's at the surface of the sun, it only takes 8 minutes to get to the Earth, but to work out from the core, it takes 100,000 to 1,000,000 years. So next time you're out there enjoying the sun's rays, think, oh my gosh, that
this
energy.
Is really coming from the sun.
Yeah, and it took all that
and
time.
8 minutes ago, right?
Yeah, 8 minutes ago, but how long did it take to get to the surface? Some 100,000 to 1,000,000 years.
Yeah. So.
Yeah, it's like old energy.
Ew.
So neutrinos. First off, how are neutrinos created? Do you remember what I said?
From the sun.
No, it's when the particles collide, they give off these little particles.
Yep, they're one of the byproducts, kind of, when during fusion, neutrino is. Are neutrinos easy to observe? Remember what I said? Nope, they're very elusive. So these are the three figures, and I'll go ahead and circle them on here. Now, no, my pen is terrible on red. So here, I'll just do it this way. The core, of course, that's where the nuclear fusion is going on. The radiative zone, that's where the random walk is. And the convection zone is like the lava lump. So you're going to want to know those for the test.
And then the convection is, you said lava what?
Lava lamp. Convection zone is like the
How
lava
I used to
lamp.
have a lava lamp. I'm a really old, like 90.
All right. So, bless you. The video you watched Friday. So, did it have, so you guys know the answers. So, do we have spacecraft that are observing the sun?
Yeah.
Yes.
They can't get too close.
But, yeah, can't get too close. We've never landed on the sun.
Mm-hmm.
And, yeah.
With a straight lava.
Right. Plasma, exactly. What?
Are they ever planning to do that?
I don't know. Like Stargate, if you watch Stargate, they harness energies of stars somehow. So I don't know. It's interesting. One of the things we have looking at the solar system is the, let's see, image. Yeah, okay. The Solar Dynamic Observatory. That's actually a pair of twin satellites that kind of give us 3D images. Mm. And then we also have another telescope out there called
the sun in the middle.
Let's see. Yes.
What's the outer?
The outer one is a single image called the SOHO, Solar and Heliospheric Observatory. Yeah, SOHO. I know that other one is called SOHO. SOHO. So if you ever say, oh, SOHO took this picture. Okay.
SOHO took
this picture. So, I have a colleague that said that their son recently said, Dad, it hurts my eyes to look at the sun. I'm like, well, no. He's like, well, no kidding, honey. You don't look at the sun because it really can damage your eyes even though you don't even know that the damage is being done.
Wow.
So, I'm just telling you.
It's been times like I see little kids just staring at the sun just to see how long they can do it.
That's not good. That's not good. Okay.
What the fuck is wrong with it?
Watch it. Solar wind. I love solar wind. We actually ran into solar wind before, about 4.6 billion years ago when our sun turned on. This is my version of solar wind, okay? So the thing about solar wind is it was created once the sun began nuclear fusion in its core. All right. What else do I need to say? Okay. So the solar wind, does this make sense? Can you kind of picture? I'll bring my sun out here. And I'm talking about how the planets orbit the sun. okay, in what we call the plane of the east, or letter E. Ecliptic, yep, plane ecliptic, so the planets orbit the sun, plane ecliptic. So the sun is blowing solar wind in all directions. It's a bubble, and it creates a bubble called the heliosphere. The heliosphere is awesome. So if I'm out here, the heliosphere goes beyond Neptune. What's after Neptune? Starts with the letter K. What's after Neptune? K. Two words.
The something belt.
Yes, Kuiper belt.
Yeah,
very
Kuiper
good.
belt.
And after the Kuiper belt, it's called the starts letter O. 2 O's.
Wait, what?
Starts letter O after the Kuiper belt. It's a spherical, the Oort cloud. Yeah, the Oort cloud. And I'm thinking this is how this goes. Beyond that, actually, is the edge of the heliosphere. So the heliosphere is where the wind from the sun actually kind of peters out.
So it's like before Pluto or after Pluto?
Pluto is actually, okay, so this is the heliosphere, this is the Oort cloud, this is the Kuiper belt, this is Neptune, and actually Pluto is in the Kuiper belt. Yep. So this actually is the edge, this is what we call the edge of our solar system. So this is a wind, this is a, okay, it kind of peters out here, right?
And then after that, it's just space.
Right. After that, it's like what we call interstellar, like between stars, space. But here's the deal. If we would have like a microorganism or something, or some bacteria from outer space, want to get into our solar system, it would have to like swim into this headspace. Yeah. So that actually is kind of a cleansing sort of thing. But that means if we do get something, okay, it is actually what's that?
It's gonna stay in the cloud, and the solar man.
Well, if it doesn't have any energy pushing it, it's not going to get in.
Oh.
So it has to have some energy pushing it to go to get us. So it must meant to get us. So anyway, that's what I think of. So this is a good figure. It has the things we talked about. In the middle is the core. This little diagram over here. You see the core, the radiative zone, this yellow, the convection zone is kind of that orange. We'll talk more about the photosphere. All right, here we are. So we have 3 parts to the inside. We have the core, the radiative zone where the random walk is going, the convection zone where the lava lamp is. Then you get to what we call the photosphere. So photosphere is right on top of the radiative zone. And then beyond the photosphere is the chromosphere, and beyond the chromosphere is the corona. So these 3 things are what we call the atmosphere. So these things are called the atmosphere. That's what I call them anyway. These 3 things are called the atmosphere. During an eclipse, so the corona is the outermost. Chromosphere, photosphere, going outward in. So during an eclipse, it's kind of fun because we get to see that corona. And so I think that's cool. What is the temperature-wise? Can you see what's the hottest layer up here of the atmosphere?
Okay. What about the outside?
Yeah, the corona is the hottest. 1 million Kelvin. And then we have chromosphere, which is 10,000 Kelvin. Then we have the photosphere, which is 6,000 Kelvin. So, and I think it's kind of complicated. I think they kind of know the answer. But why would it be farthest from the sun that you're the hottest? And it has to do with kind of how the energy is going to track there. I think that's pretty cool. So these guys, these 3 down here, I'm going to write. I wrote atmosphere up here. These 3 guys, core, radiation zone, convection zone, I'm going to put in inner, okay, or interior.
You said core.
Yeah, core, radiation zone, convection zone. Those are some characteristics about those. Now, those are the one thing about those slides, they're so small. When I printed it, when I used to print them routinely for students, they're like, Mrs. Dodge, can you make them bigger? I'm like, oh. So you guys got the small version. All right. What else do we need to know? So starting with the photosphere. So first off, is the photosphere part of the interior or is it part of the atmosphere?
The atmosphere.
Part of the atmosphere. And it's weird, I say it's part of the atmosphere, but it's kind of a little bit associated with, the surface. The photosphere is kind of more the surface than the atmosphere, so you just have to bear with me. The photosphere. When we glance, never look, but if you glance up at the sun, the layer you're seeing is the photosphere. It actually sends us the visible light that we're seeing, photosphere. All right. You mentioned the thing about the sun being like I don't know if you said gas or liquid. It's actually between a gas and a liquid. The sun is called plasma, and it's actually kind of similar to our plasma TVs. So it's just hot, charged, ionized particles. So that's what makes up the sun. So you're looking at glancing at what we call the disk of the sun. We've talked about the disks of the sun before, because when we talked about that's the sun and the moon, from our perspective, the disk of the sun and the disk of the moon are about the same size. You would imagine as you're glancing into it that you're looking into the hottest region, and can you kind of see that light orange there?
Yeah.
Okay, that light orange, which I don't think we could see with our naked eye. You should never look at this one like this. But kind of that darker orange is kind of a cooler part of the sun's disk, okay, called the limb.
If we do look at the sun tomorrow, is it gonna be like in a lens over it or something? Or?
Yeah. So tomorrow, and if it's not tomorrow, hopefully it'll be the next week. Or if we can't catch it then, I'll have to do it on maybe Friday. But I have one like sunglasses. It's just like sunglasses. I put over the end of my telescope I've had out before.
Yeah.
And then the other technique is called eyepiece projection. So basically you take the sun's light through the eyepiece and you take the eyepiece and you put it on a piece of paper. So you can see the image of the sun projected. So that's two ways. Oh, there's a third way, and it's called the gold telescope. It's like Goldfinger. And so anyway, it's actually meant to look at the sun. It's a solar scope. So three ways to safely look at them. So the photosphere, I know I said it's part of the atmosphere, and this is going to be kind of weird, but the photosphere is the thing that we see when we look at it, and it has these things called granules, and I think I'm going to show you this class kind of reinforces that. Yes, Earth's pretty darn small. So this is the lava lamp I was talking about, and the video you saw, I know these are circles, but were these are granules. They weren't all circles, were they? They kind of had different shapes and sizes. But you see hot coming up, and then it cools down and it falls back down, kind of like the little, I still think beehive. There's the granules. Now, these are not granules. Well, yes and no. This is a close-up, and we'll be talking more about this on Wednesday. This is a close-up. You see, these are granules. This is like granules, maybe. This is actually called a sunspot. These are sunspots. These are blemishes on the sun that actually are not always there. Granules, always there. These are called sunspots.
The sun got burnt marks.
The sun has kind of cool regions.
So that part is the cool region thing?
Yeah. The black parts that look burnt, those are cool regions.
Reverse psychology.
It is reverse psychology. So where's a sunspot, left or right? Right, yep. That's a sunspot. But kind of behind kind of the background of sunspot, those are granules. So granules are always there. I'll put always with granules. And sunspots are just sometimes. How many more slides do we have left?
Like 3, I think.
3?
Yeah. 3.
Okay. Well, I think we'll take a running start at this. I know we only have 3 slides left. You have enough to go ahead and do this if you want to. Remember that I gave you out the questions that were due for Unit 3. And I'm going to do the same thing like I did last time.
Extra credit?
Yes, extra credit, turn them in. But since we didn't finish this part, these wouldn't be due until before Friday. Does that make sense? Because we got to finish it, and then you turn it in for 11
Probably
points.
be Wednesday.
No. She
No,
said
because
because we gotta finish it
Yeah.
Wednesday.
Yeah, we're gonna finish it Wednesday, and then you'd have till Friday. Yeah.
Okay.
But I think on Friday we'll probably finish up the sun, maybe even start on, on Wednesday. All my days are almost up.
Yeah, too. I don't know.
Yeah. But, so they would not, you don't have to turn them in, and since we didn't do them till Friday for the 11 points.
Okay.
But I think on Wednesday, I think we'll get through, we'll finish both parts of the sun.
Okay.
All right, that's all I got, guys.